Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. In the name of Allah, the most gracious, the most merciful, we start our scientific seminar that is entitled Non-Vacuum Process Thin Film Chalcogenide Material for Photovoltaic Applications by Dr. Wيلمان سيبتينا. Dr. Wيلمان سيبتينا is a researcher in Hawaii Natural Energy Institute in Honolulu, United States of America. He has extensive experience in solution-based processing of thin film, chalcogenized for application in the thin film solar cells and solar fuels. Currently, he is performing research on the printed chalcogenides for photovoltaics and photoelectrochemical water splitting. He gladly accepted the invitation made by our Committee of Scientific Research in the Department of Physics. And we are more pleased to have this opportunity with him. So you may start now, Dr. Wيلمان.
Okay, thank you, Ms. Hester, for the introduction. Allow me to share my screen.
Yes, go ahead, please.
Share. Yeah. Let me switch. Yeah, would you be able to see my screen right now?
Yes, it is very clear.
Okay. Thank you. Assalamualaikum warahmatullahi wabarakatuh. It's an honor for me. It's a pleasure for me to be able to present some of our works. And the title of my works, my presentation today will be a non-vacuum process thin film chalcogenide materials for photovoltaic applications. So I have been doing this topic since my graduate study, my master, my PhD. Up until now, my research is always related to this non-vacuum process chalcogenide thin film solar cell. So the talk today will be some of my past works and also my recent work as well. And here's the outline of the today talk. So first I will briefly introduce you some overview of thin film photovoltaic. And then after that, I will enter some of our published work on earth abundant chalcogenide materials for thin film photovoltaics. And then I will enter some of one of our recent work here in Hawaii. It's in situ alumina passivation for printed copper indium sulfoselenide solar cells. And last, if I have enough time within my 1 hour time slot, so I will also introduce some of the works on semiconductors or solar cell for photoelectrochemical hydrogen production. Let me change my pointer first. Okay. Yeah. Okay. Before I getting into my main talk, so I would like to introduce you to the place that I belong now. So I'm working now on the Hawaii Natural Energy Institute. It's an institute research unit belong to the School of Ocean and Earth Science and Technology at University of Hawaii. So the research institute is mainly doing research on natural energy, which could be of interest to the state of Hawaii in more specific, because as you know, the Hawaii is located in the Pacific Ocean, so they have their own unique challenges. So the research of the energy research there is more specifically directed to the interests of the state of Hawaii. So for example, the research that the institute working on are alternative fuels such as biofuels, hydrogen, methane hydrates, or electrochemical power systems such as fuel cell or battery, and also renewable power generations, photovoltaics, ocean energy, or also on the energy efficiency such as seawater air conditioning, or also more, and also on the bigger scale such as the grid, smart grid, and microgrids. And the place that I'm working on right now, so I belong to the thin film labs. So we are doing various research such as quantum dots and also solar cell lift-off. So this solar cell lift-off is specifically interesting for the application as a tandem solar cell, multi-junction solar cell, where usually we combine different solar cells to maximize the solar spectrum. But another way is that we can pre-made the solar cell and then we lift off the pre-made solar cell and then combine it with another solar cell later on. So that's the meaning of the solar cell lift off. And also the printable photovoltaics. So we are using molecular inks to be able to print it. And also thin films or solar fuels generation, specifically for hydrogen production, and also nano photocatalysts. And right now here I'm involved in these 3 projects. So I'm involved in the lift-off, solar cell lift-off project, the printable photovoltaics, and also the solar fuels generations. So now I get into my main talk. So I will talk about some of the overview of the thin film photovoltaics. And as some of you might already know that there are different kinds, various kinds of photovoltaic technologies. And usually it's categorized into three groups. So the first one is a wafer-based silicon. So it's the most widely used solar cell or solar module right now. And it's a rigid, made from a silicon web, is cut out from ingots. And the technology is relatively mature, and it has proven to has long lifetimes as well. So inside there is a monocrystalline silicon, and there is also a polycrystalline silicon. And the second technologies, which some people usually call it the second generations, is the thin film photovoltaics. So here, unlike the silicon solar cells where it's quite thick, we can deposit the film in a thin films, so quite thin, and we can choose many kinds of substrates as well. And there are a high cost reduction potential. So we'll talk more about this later on. And also low energy payback times. So energy payback times means the amount of the output energy that is produced equal to the amount of the energy to make the solar cells. So if the solar cells can produce energy faster than the energy that is needed to produce it, so that means it has a lower energy payback times. So inside this, there are amorphous silicon, there are cadmium telluride, and copper indium gallium sulfoselenide. So I will talk more about this later on. And the next technology is emerging photovoltaics. So this is basically the technology that is not yet commercialized, but also promising and has maybe new concepts. So it's promising, but still immature in the technologies, new materials or concept, and the efficiency or also stability are not yet proven. So some of the examples are organic photovoltaic, dye-sensitized solar cell, or quantum dot, and also this is the hot topic right now in the solar cell field. The perovskite solar cell also belong to this emerging photovoltaic. So why the thin film photovoltaic is interesting, or is also has a huge potential? First is the high cost reduction potential. So unlike silicon solar cell, as I said before, the silicon solar cell is usually quite thick because of their low absorption coefficient, as well indirect band gap, and it typically around 200 to 500 micrometer. But for the thin film solar cell, it can be as thin as 1 micron. So the whole stack can be as thin as 1 micron, maybe minus the encapsulation. And we can fabricate the material using various fabrication methods. We can do physical deposition, a vacuum based method, such as the sputtering, the evaporation, and molecular beam epitaxy, for example. Or we can also do a non-vacuum one, which is I have been doing this one, such as the ink. The ink can be printed or can be sprayed, or also electrochemical deposition, electrodepositions. So this belongs to the non-vacuum one. And also it's possible to do a monolithic integration. So in silicon solar cell, usually the way to make a large module is by combining different wafer. So it's called wafer bonding. But in thin film solar cells, instead of combining different cells all together, so we can make a huge area of the solar cells, and then we can cut it using a laser so that we can have a series connection. So it's called a monolithic integration. And also it's possible to do a roll-to-roll processing, which potentially can make a quite cheap production cost, because it's possible to do on a flexible substrate. And second reason is the flexible choice of substrate and also shapes. So we can do the fabrication on glass. So this is more suitable for roof, for example, or the utility application, or stainless steel, or also polymers if you want to make it a flexible, or such as like in the bag where we need some certain shapes, or ceramics. And also we can make some costume design, because in thin film solar cell, basically we can cut them using a laser, so we can make any kinds of shapes basically. And another reason is for the aesthetic point of view, especially for the building integrated PV or BIPV. So because in silicon solar cell usually has blue color, as you might already know, but thin film solar cell usually black in color, so it's more pleasant to see in the eyes. So for example, this is the building in Germany. So Manz is one of the companies that produce thin film solar cells. So they use the thin film solar cell on their building. And also this is one of the office in Sweden, which also use some CIGS solar cells on their wall. And also here, some of the flexible solar cells as a roof also. So it's a more aesthetic compared to the silicon solar cell. And from efficiency point of view, so they are already quite high efficiency. So the CIGS for the cell is already reach more than 20%, close to the silicon solar cells, and the cadmium telluride as well already over 20%, and the module is close to 19%. So the high efficiency are already demonstrated for the thin film solar cells. And so here's a more detailed looks on each of the technologies for the amorphous silicons. So the low cost already demonstrated, and they are using earth abundant elements, but the challenge for this is the instability. And also the efficiency are still medium, even if we make a multi-junction solar cell. Medium, it's range, I think 14 to 15% for the multi-junction solar cell using amorphous silicon. And for the cadmium telluride, it's already proven a high efficiency solar cells, and it's also low cost. But inside there is a tellurium, which is a scarce element, so not abundant. And also they are still using cadmium, which considered as a toxic and contaminant substance. And also CIGS. So this is the one that I will be talking more deep on this talk. So it already has high efficiency and relatively low cost. However, the indium and also the gallium are a scarce element, And one of the alternative material is CZTSSE, which also I will talk this about more later on. So this is in short how is the working principle of the thin film solar cells. Basically, it is similar with the silicon solar cells. It's a combination of a PN junction. But the difference is that in the silicon solar cells, we dope the silicon either using boron or phosphor to make it P or N. But because of the difficulty of making N-type for most of the thin film absorber, so usually we pair it with another material. So for example, here in CZTSSE or CIGS also, they pair it with cadmium sulfide. So this is the most widely used right now. It's still using cadmium, unfortunately, but a lot of research also now undergoes to replace the cadmium with another more abundant or not toxic materials. But yes, so it's a heterojunction solar cell basically. So here's the Venn diagrams for each of the semiconductors. So as you probably already know, so as a when we contact the p-type to n-type, because the charge imbalance, so there will be transfer of charge between the p and n until the energy is equilibrate, and then it will make a electric field or bending here, which we call it the space charge regions. So the electrons upon the absorption of the sunlight, the electron hole pair will be created, and the electron will transfer to the top contact. So the top contact, this is the aluminum doped zinc oxide, and the hole will transfer to the molybdenum glass. And one of the important parameter in the heterojunction solar cell is this difference of the energy levels, because in homojunction solar cells we usually don't have this different energy level, so the electron transfer is quite smooth. But because we are using heterojunction, so the choice of the n-type material is very important. So we don't want the electrons on the conduction band level to have a barrier. So we want the barrier to be as low as possible here. So CDS has a little bit higher conduction band level, but it's still sufficient to the electron jump transfer through to the top contact. So that is in short the working principle. And also, because later on I will be talking about the JV curve. So just some brief explanation about the JV curve. So we usually characterize the PV by using a JV curve. The efficiency is as a function of the VOC. So VOC, this is the JV curve, current versus voltage, and the VOC is the maximum voltage that can be drawn from the solar cell, and then multiply the GSC, short circuit current density. So the current when the voltage is 0, and then multiply the fill factor. So the fill factor is basically the measure the squareness. So the ratio between the area of the A here, for example, and the ratio divided by the area of the B here. So the GSC multiply the VOC. So that gives the fill factor. So if the area is smaller, then the fill factor is lower. So if this area is bigger, the fill factor is bigger, and then divided by the amount of the power of the light. So that's just to give you some short background of the IV curve. And now I will get into some of our result. And this is about abundant chalcogenide materials for thin film photovoltaics. So chalcogenides refers to the materials containing chalcogen elements. Chalcogen means the sulfur, selenium, or tellurium. So the work here, mostly we did it in Osaka University, Japan. So now some of the background. So I already talked about this before, that the CIGS and cadmium fluoride are the two dominant FIFI technologies. Their efficiency already reached above 20%. However, if you see the graph here, this graph showing the reserve of the some of the elements that are being used in thin film solar cells, and also price here in US dollar per kilogram, you will see that the gallium, the price is quite high, and also the indium, also the price is quite high, while the cadmium and the cadmium is also quite toxic. So in the community, there is a need to find new photo absorber materials which are inexpensive, abundant, and environmental friendly. So how to find the materials that are suitable for solar cells? So there are multiple considerations. So the very first thing that we usually consider is the band gap. So the band gap will determine what is the cutoff for that material to absorb the solar spectrum. So because we want to absorb the visible light as much as possible, so usually we are looking at the materials with the band gap energy around 1 to 1.8 electron volt, and with the optimal band gap around 1.1 to 1.5. And also consideration number 2 is the absorption. So we want the material to have a direct band gap and also high absorption coefficient. So we can use the materials, only thin material. We can use the thin material, so no need to be a thick material. And those two, usually we use it for experimentalists. So I'm experimentalist. So usually I consider these two before preparing the samples on the lab. But recently, there is also rise in competition. So now we are also looking more into the defect. So this is very important, the defect, but now we are getting more sophisticated and more details on the analysis of the defect. So the defect here means the electronic defect, not the physical defect such as cut or something like that, but this is more to the electronic defect. So for example, that this is the CZT-SSE material. So it's a naturally a p-type material because of the copper vacancies is quite shallow here and has a low formation energy. So we don't want any mid-gap defect basically. So because usually mid-gap defect will act as a trap for the electron hole. So we want to avoid a material which has a mid-gap defect. And also last is the suitable energy level. So because it's a heterojunction solar cell, so we want to have a good P and N type pair. So we want to find a material that has suitable conduction band alignment between P and N type. And so what are the candidates for the photovoltaic? So basically in the community, we divided the classes into 4. Oxides, for example, it contains, the material contains oxygens and chalcogenides. So this is the one that I will be talking today. So it contains sulfur and selenium. Or halides contain brome and iodine, and also pnictides contain nitrogen and phosphor. So some of the materials listed here have reported to have efficiency more than 3%, so it's work. There are more materials, but also due to the difficulty in making it, so it resulted in a not so good efficiency. So here's some of the materials that have at least more than 3% efficient. So for example, oxide, the copper oxide or bismuth iron chrome oxide, or the chalcogenides. There are lots of materials on this class, and I will be talking more on this copper antimoney sulfoselenide and copper zinc tin sulfoselenide, or halides here, for example, bismuth iodide or cesium lead bromide or iodide, or cesium tin bromide and cesium tin iodide. So now I will get into why the copper zinc tin sulfoselenide is interesting materials. And so basically the copper zinc tin sulfoselenide is a replacement of the indium and gallium group 3 materials, and replaced by a combination of group 2 and group 4 zinc and tin, which are more earth abundant. So the crystal structure is a derivative from a zinc blend structure, which is similar with silicon, cadmium telluride, or copper indium gallium selenide. So all of them have high efficiencies. And some of the characteristics are they have a suitable band gap for solar absorption. So the band gap is around 1 to 1.5 electron volt, depending on the sulfur to selenium ratio. So we can adjust the band gap depending on this ratio. Also, they have a high absorption coefficient. So we only need a thin material between 1 to 2 micrometer. And they are non-toxic, and also has a good chemical abundance. So here's the typical fabrication steps that we are doing on the lab, on my lab here in Hawaii, or also in my previous labs. So we typically start with the preparation of the molybdenum coated on the glass. So molybdenum is chosen here because they have a good ohmic contact with most of the CIGS or CZTS materials, and they don't make an alloy with them, with the metals. So we typically use a molybdenum around 700 nanometer, and we usually fabricate by DC sputtering, or also if we cannot fabricate this, sometimes we also order outside commercially, because it's also it's widely available. We can buy as well. So after that, we deposit the precursors. We contain the copper, zinc, tin, sulfur, or selenium, for example, or any other material that elements that can be we want to include. So there are various methods to do this one, and I will be talking more on the ink and electrode deposition here. And after that, because it's still low crystallinity, so we want to make a high crystalline materials, and also we want to introduce the sulfur or the selenium. So we do a process called sulfurization or selenization. So this is typically done in either in ampule or in a furnace together with the sulfur or selenium sources. And then after that, the N-type material, the CDS, we use a chemical bath deposition. So right now, even in the industry, so chemical bath deposition is still the high performing one. And after that, we deposit a bilayer of the zinc oxide and aluminum doped zinc oxide, or we can change this one to any kind of TCO, for example, ITO also is possible. So this act as a top contact, window layer and the top contact. And then finally, if we wish, so we can also deposit a aluminum grid as a current collector to collect the current. But sometimes also we just measure the solar cell up to the aluminum doped zinc oxide or TCO because it's already conductive. But if we wish also, we can add more aluminum grid to correct the current. So this is typically the solar cell, the image of the solar cell on the lab. So these fingers are the aluminum. So this has 7 cells altogether for this one. And so I will get into more of our results on electrodeposited CZTS and copper antimony sulfide. And so so we fabricated the CZTS and copper antimony sulfide by first electroplating of the metals. So we electroplated the metals, and then we do a sulfurization to convert them into the sulfide. So this method, it is quite convenient to control the final composition, because the composition of the ratio is quite important. So it's quite convenient by this method by adjusting the amount of deposited metals. And here's some introduction maybe for electrodeposition. So it's a quite low cost method. So we basically need a potentiostat and also a beaker with the solutions inside. So the potentiostat will make a different potential. Will create a different potential between the working electrode and the counter electrode here. And they will force to make a reduction of the ions into metals. So it's a non-vacuum method. It has low equipment cost and also low temperature. So usually we do it at room temperature, and it's suitable for large scale and already established in industry. So industry already use this a lot. For example, here some picture on electroplating of copper, and for PCB, for example, or this is electroplating of nickel for many kind of application. For example, the automotive. So it's already well established method in the industry. So first, for the ZTS fabrication, so we use a 3 electrode systems, working molybdenum on the glass as a working electrode, and then AgCl as a reference electrode, so as a reference for the potential, and the counter electrode is the platinum. And then we electrodeposited copper on the top of the molybdenum, and then tin, and then after that the zinc. So the sequence here is chosen because each metal has different reduction potential, and copper happens to have a reduction potential that are more positive, more easier to electrodeposit. So we don't want to oxidize the bottom layer. So this sequence was chosen so that there are no oxidation occur on the bottom layer. So then finally, this sequence is chosen: copper, tin, and zinc. And we adjust the amount of the metals so that the ratio of copper to zinc to tin is 0.8. So it's slightly copper poor, and then zinc to tin is 1.2. And then, so first we did direct sulfurization. So we sulfurized directly the metallic stacks. So the way we did it was we put an ampule together. Inside there are sulfur powder as a sulfur source, and then the samples. So we evacuate the ampule and then we close it. So the inside ampule was in a vacuum condition. So, and then we put them in a furnace at 580 degrees Celsius for 10 minutes. So here the SEM images of the sulfurized film. This is ZTS film. So as you can see, there is still quite rough, and there are the formation of large voids, and because we thought that because of the volume expansion of the copper sulfide. I will talk more about this later on. So it's still not yet sufficient for absorber. And then, so what we did some preheating treatment. So instead of sulfurizing directly the metallic stack, we did a preheating. at 350 degrees Celsius for 20 minutes in an ampule, but without the presence of the sulfur powder. So it will make an alloy. It will make an alloys. So for example, here's the XRD. So this is the XRD of the metallic stack. We see the copper and zinc and tin reflections. So then when we preheated the metallic stacks, we didn't see the reflection from the metal anymore, but the alloys. So copper tin alloy or copper zinc alloy. So we made an alloy by this approach. And then the alloy was sulfurized using similar method to make a CZTS. And here bottom picture as the comparison of the without preheating and with preheating. And we can see with preheating, the film now become dense and also no formation of the voids. And the maximum efficiency, so this is the JV curve that I mentioned before. So the maximum efficiency that we could get at that time was 8.1%. And the record for the CZTS right now is 11%. It's still low compared to CIGS because of some challenges, but what we got was not far off from the record. So it's but still under development as well. So we also try to synthesize copper tin sulfide using similar method. So the copper tin sulfide is a interesting material because it has an absorption coefficient, high absorption coefficient. The band gap is also quite suitable for solar absorber, 1.5 to 1.6 electron volt. It's also non-toxic, and antimony is more abundant than indium. However, no report on copper antimony sulfide with appreciable efficiency. So we tried to synthesize copper antimony sulfide using similar method. So we electroplate copper, and then on the top of that, we electroplated antimony. So here's the SEM, cross-sectional SEM image. So this is the molybdenum, and then you can see the copper layer, and on the top of the copper layer is antimony layer. So then we perform preheating to the copper antimony metallic stacks. But right now this one we didn't use the ampule because we found out the ampule was not so effective for the copper antimony sulfide. So we use a tube furnace with a constant flow of argon, and when we perform the alloying at 510 degrees Celsius for 60 minutes, so it's a bit higher than for the CZTS because the melting of the antimony is also higher, a bit higher, and also we want to make sure that we form the alloy. And here's the XRD image, XRD spectra of the copper antimony metallic stack. You can see a reflection coming from the copper and coming from the antimony. And then when we preheated, some of us make a copper antimony alloy with still antimony reflection remaining. And here are the images. So this is, I show it already before. So this is the preheated one. You can see that the metallic stacks are combined into an alloy. So now we compare the XRD of without preheating sample and with preheating. So we sulfurize both of them. So this one we sulfurize using hydrogen sulfide in a tube furnace with the argon flow and hydrogen sulfide flow. And if we did it without the preheating, we still observe some reflection from antimony sulfide here. While if we do the sulfurization from the alloy, there are no reflection from antimony sulfide. So all of them copper antimony sulfide. And here's the images from the without preheating and the with preheating one. So same with the CZTS research that I showed you before. We observed a formation of the void if we did it without preheating, and also pinholes. But if we do a preheating, so the film is denser and more suitable for solar cell. And here's the proposed mechanism. So if first is this, if we directly sulfurize the metallic stacks, so what we thought is that once we sulfurize, there will be a formation of copper sulfide on the bottom part where the copper is, and antimony sulfide on the top. And then the formation of the copper antimony sulfide is by the solid state reaction between them. But because of the high diffusion coefficient of the copper, so it left some of the void on the interface. And then once the time goes on and then we prolong the annealing, the copper antimony sulfide will be formed, but there will be still isolated copper sulfide and antimony sulfide remaining on the film. While if we did the preheating first, so we make sure there are alloy formation of homogeneous alloy, and then if we sulfurize, so the reaction of the solid state reaction between copper sulfide and antimony sulfide happens homogeneously everywhere. So we can make a more homogeneous copper antimony sulfide. So the preheating basically is to minimize the formation of the voids and the pinholes, and also to enhance the formation of copper antimony sulfide through the more homogeneous reaction of the binary sulfide, which are antimony sulfide and copper sulfide. And here we compare the JV curve. So the with preheating and without preheating, as you can see that most of the solar cell parameters are increased. So the GACR was increased, the fill factor was increased, the VOC was increased, and we were able to get efficiency 3.13%, and the record right now is 3.2%. So it's still quite low for the copper antimony sulfide. Yeah, because of some of the intrinsic electronic properties. But with the electrode deposition, we're able to match the record efficiency, which was made, I think, by nanoparticle ink, if I'm not mistaken. So here's the summary of the first part. So we did the electrode deposition of stacked metals to fabricate CZTS and copper antimony sulfide. And then we performed preheating to the metallic stacks. And we were able to get a film with good compactness, homogeneity, and adhesion. And the solar cells from CZTS and copper antimony sulfide, the efficiency were 8.1% and 3.1%. And so I will talk now more about our recent work here in Hawaii. So the title is the In situ alumina passivation for printed copper indium sulfoselenide solar cells. So yeah, we are still using the indium here because we want to prove a concept, but also we are interested to apply the method, the passivation method, to a more abundant material as well. So just to give you some of the background, so the passivation means the suppression of recombination losses. So here's some illustration. So in semiconductor, when the semiconductor absorb light, so it creates electron hole pair. So ideally, we want the electron to flow to the respective contact and hole flow to the respective contact. But in most of the cases, we usually have a recombination. So instead of flowing, so the electron and hole are recombined, mainly through surface defects. So the passivation means the suppression of these recombination losses. And the semiconductor surface potentially exhibit high concentration of defect because of some of the disturbed chemical bonds, or also exposure to hostile environment. So the strategy that routinely used in silicon solar cell, so the strategy is borrowed from silicon solar cell, actually, is using thin films to reduce the recombination. So here's, for example, on the silicon. So it has a lot of surface defects, and then they put alumina as a dielectric layer, and then the surface defects they observed that the surface defect was reduced, and then if they did a further thermal annealing, so the surface defect were also even more reduced. So they call it a chemical passivation. And another effect is they call it the field effect passivation. So because the alumina, so they observed that alumina has a negative charge density. So because of that negative charge density, they could repel the electrons, the minority carriers. So there will be less recombination on the interface here because of the electron could be repelled by the alumina. So that's what they observe on the silicon solar cells. So yeah, the alumina passivated solar cell already being used in silicon passivated emitter and rear contact. So in short is PERC cell. So they put alumina Al2O3 on the bottom part near the P-type P plus silicon, or also in CIGS recently also they tried to coat them with alumina on the bottom. So the method that is usually used called atomic layer deposition, or ALD. So it consists of multiple pulls, so of a monolayer of precursor, and then pulls again with water. So it's a gentle process. It's a gentle process. So we are able to build the material quite gentle, and also it's more homogeneous, but also at the same time it's a costly process as well. So in this research we are able to synthesize copper indium sulfide selenide with alumina, which we thought acted as a defect passivation, but not using ALD but using a molecular ink. So instead of ALD, we're able to get alumina using molecular ink, nanoparticles everywhere here. So here's the fabrication step. So we fabricate the material using molecular ink. So we dissolve the salt, metallic salt, the copper chloride, the indium chloride, the aluminum nitrate as the aluminum source, and thiourea as the sulfur source, and then we dissolve them together to get this clear solution. And then the method that we use is spin coating. So we spin coat this ink on the top of the moly, and then we spin coated them around 10 layers to build the thickness to make so we call it AL minus CIS. So CIS with the aluminum inside. And then we selenize them to make a crystalline CIS SE. So here's the XRD of the as deposited. So the spin coated film is shown in this black color here, and then the selenized here is shown in the red color here. So as you can see that the as deposited is still low in crystallinity, and then once we selenize, we observe an increase of the crystallinity significantly, and also we observe a peak shift. So this shift is due to the replacement of the sulfur with the selenium. So because of the sulfur, selenium has a bigger size atom bigger atomic size, so it's shifted the XRD to the lower angle. So, and then we compare the XRD of the 112 peak. So this is the 112. So we getting closer. We zoom in the 112 peak, and then we compare them with the sample without aluminum, and we see that there is no significant shift. So the aluminum doesn't make an alloy with the CISSE. So because if we observe a peak shift to the right side, usually then there's potentially alloying, but we didn't see that. So there are no aluminum alloying here. And then also when we measure the reflectance of the film, so the band gap from both of them are relatively similar, 1.01 electron volt. And then we observe the compositions by using Auger electron spectroscopy. So we measure the depth compositions, and so each color represent each metals. But what I would like to emphasize is the aluminum shown in this blue color, and also the oxygen shown in this orange color. So we do observe aluminum along the bulk and also more on the surface, as well as the oxygens. And if we compare only the oxygen signal between the CISSE, so the sample without aluminum and the sample with aluminum, we see that there is no oxygen on CISSE. While we observe an oxygen on CISSE. So the aluminum is distributed throughout the film for the sample with aluminum, and also still there is some amount of oxygen remain throughout the bulk of the film. So then we look by TEM to see more image of the film. So here's the cross-section TEM image of the film. This is the molybdenum here, and then the CISSE here. And as you see that there are two contrasts. One is the bright white, and also the black one. So when we zoom in at these red dotted squares, and then we measure the EDX, so the atomic composition of that, we saw that it's in fact is alumina, Al2O3. And then so when we do the diffraction to those spots, it's basically an amorphous sample, while the surrounding is from the CIS, so it has a ordering pattern of crystalline film. And then so when we zoom in at this yellow area, for example, on the surface here, we see the aluminum Al2O3 is also existed on the surface here. Or also if we zoom in at these green areas, we see also the alumina Al2O3 is also existed there. So it's basically exists everywhere, spreading everywhere. And then we compare the solar cell properties between the sample with and without aluminum oxide. And so we made more than 15 cells from each of them to give a more statistic. So we want to avoid any sample to sample variation. So we made lots of cells to compare the trend. So first is this graph showing the efficiency of that several cells. And as you see that the efficiency in general, the efficiency of the sample with alumina is increased compared to without. And the short circuit density, the GAC, is relatively similar. Well, slightly increased, but in general, it's similar. And also the VOC open circuit voltage is, as you can see, is increased. So it can represent a more better junction, less recombination, and also the fill factor also is boost. So it's also show less resistance sample, less recombination. And then we compare the best JV from each of them. This the red one is with alumina. This is without. So the efficiency that we can achieve is 11.6%, while the maximum one from the without sample is the 8.3. So it's a significantly increase. And this graph also shows more deep. So this is the EQE is the external quantum efficiency. So it's measured the amount of the electron extracted, current extracted from each of the photon from each of the wavelength here. So as you might notice that it's relatively similar onset, but is slightly higher across the entire wavelength, which explain the slightly higher short circuit current density from the sample with aluminum. So then we also get the characterize more on the electronic properties. So we want to know the defect properties of the material. So we measure the capacitance, and then from the capacitance we extracted the doping density or the defect density according to this calculation. So this is the defect density or acceptor density, and the X is the space charge region according to this equation, which is represented here on the x-axis. So what I would like to emphasize is that we measure several cells, and then we average the doping density at the equilibrium condition at 0 volt, and then so it has a reduced defect density for the sample with aluminum, while CISSE is slightly higher, the defect density here. And also the space charge region is also increased compared to the sample without aluminum here. So it's as one of a proof also for the effectiveness of the alumina. And also we did the temperature dependent POC analysis to see the recombination mechanism. So according to this relationship, so we want to look at the EA is the activation energy for the recombination. So according to this relationship, if we extrapolate the T, the temperature, towards 0, ideally we should have a VOC equal to the activation energy. And so if the sample has a lower activation energy, means there is the sample or the junction is limited by some interface recombination that what we can extract from this. So what we observe is that although there are some maybe plus minus inaccuracy, but what we observe is that the activation energy for the CISSE is lower than with aluminum. So the lower activation energy could reveal a more severe interface recombination on the CISSE. And that's also, we can say that the sample with alumina has a superior interface, superior CISSE CDS interface. So here's the summary of this part. So we able to get a fabricate CISSE thin film with incorporated with nano size amorphous alumina, and we could get a maximum efficiency of around 11.6%, higher than without alumina. And we thought that the improvement of the efficiency was because of the defect specification with the capacitance and the temperature-dependent VOC analysis as a proof. So we show a decreased interface and bulk recombination. Although some more deeper study is still required, especially to explain why the mechanism of the passivation. Is it similar with the ALD quoted, or is it is maybe different? So we are still doing this complementary analysis. And I think I still have some 3 minutes maybe time to finish this talk. So I will just briefly introduce some of our result on the solar cell for PEC hydrogen production as well. So I already talked about, so we can convert the solar energy into electrical energy by using PV to get electricity, but also as a way to maximize the solar energy. Also, we can convert the solar energy into a chemical energy, for example, hydrogen. So we can do it through a system called PEC or also electrolysis by using FeFi. So it's some kind of energy storage as a chemical bond. So the reason is that actually the visible light has a sufficient energy to split water into hydrogen and oxygen, but it requires a combination of light harvesting system. So a semiconductor, for example, a photoelectrode in this graph, and a water splitting system. So the anode and cathode as a catalyst. So it is possible to convert directly solar energy to chemical energy. So the technologies to produce the hydrogen by using solar. So one is that we can make a series of PV and then combine it with electrolyzer, but this is considered as a expensive method, although the technology are readily available. Though the more lower cost one is BEC. So instead of wiring the solar cell, we can immerse the semiconductor inside the solar cell. But the technology readiness is still low, and we are still on the basic research. And so the ultimate target is to be competitive with the price of hydrogen from steam methane. And so as a measurement of the efficiency, we usually use STH, so solar to hydrogen efficiency, by using this equation as a function of GSC. So in summary, we need a combination of solar cell or semiconductor with 1.6 volt, or also STH directly to the GSC. So this is the system that we are using, combination of photoanode and photocathode. So the photocathode responsible for the hydrogen production, and photoanode is for the oxygen. So this is the image of the design of the realistic design. So just to give you a brief result, so same as solar cell, we measure the JV of each of them. And then what we did is we try to combine CIGS and bismuth vanadate as a photoanode. And then we synthesized the material by using spray pyrolysis. So we made a different CIGS with different gallium concentration. And then we made cells using CDS, but we deposited platinum as a catalyst on the top. And then we observe change of band gaps with as a function of gallium, and then the band gap is increasing as the gallium increase. And when we observe by XPS, the valence band is deepened. So it's the mechanism for the improvement of the band gap. And then we sandwich, we make a tandem cell. So this is for the CIGS, and this is for bismuth vanadate, and the intersection here is the operating current, and we were able to get operating current around 1 milliamp, which is equal to close to 1 STH, solar to hydrogen efficiency. And yeah, I think I don't have time to, this is also for the lower cost systems, antimony sulfide, we also did measurement, we also did fabricate using a lower cost system. And yeah, we dig more into the electronic properties, and also we measure the stability, and we saw that it's quite stable after reapplication of some of the catalysts. And yeah, so last, I would like to acknowledge some of the groups where we did the experiments. So Prof. Matsumura and Prof. Ikeda at Osaka University, Japan, and here Dr. Gaillard in University of Hawaii, and in Switzerland, University of Zurich, Prof. David Tilly, University of Zurich. And also thank you all for your attention. And I'm very happy if you have to answer some of your questions. Thank you.
Thank you so much, Dr. Willman. I would like to share the screen in order to share the certification of appreciation. Could you please stop the screen share?
Yeah, stop share. Yeah.
Thank you so much. All right.
You're welcome.
So here presented by the Vice Presidency for the Postgraduate Studies and Scientific Research, the College of Science and Humanities in Jubail extend its sincere gratitude and appreciation to Dr. Wيلمان Sibtina for presenting an online panel discussion entitled Non-Vacuum Proceed Thin Film Chalcodonide Materials for Photovoltaics Application. Thank you so much, Professor Wيلمان. Inshallah, this certificate of appreciation will be sent through your email. Right now, we're gonna proceed into the Q&A sessions, and I got many questions, honestly, on my private. So I'm gonna start to ask these questions. I'm gonna start with the first question. Besides to the electronic part regarding the defect filters, do defect filters require programming to be made and installed within a PV system?
Within a PV system?
Yeah.
I'm not an expert on the computational, but it's usually as a separate study. It's not installed within the PV system. So it's separate from the PV system for the defect. So it's a separate study, not embedded, not embedded in the PV system, but it's a separate study.
All right, thank you so much. Second question was, which was the best growth technique you used in your labs to grow the solar cells you presented?
The highest performing one is the electrode deposition. Yeah, because the other solution best technique, for example, the spin coating, because it's come from solution, so usually it has some carbon inside from the solvent, so it's not 100% pure, but the electrode deposition is pure. So we use a metal, so it's metal, no carbon, so it's more pure precursors. So then it resulted in a higher efficiency. So yeah, electrode deposition is more efficient.
All right, thank you so much, Dr. Wيلمان. Third question, what's the difference between RC sputtering and DC sputtering when it comes to growing the suggested solar cells?
Yeah, for DC sputtering, usually we use it only for metals, molybdenum or aluminum. Yeah, only for metals. But for the metal oxide, for the ITO, or also zinc oxide ceramics, we use RF because it's more. We were able to control more of the growth. So yeah, for the DC, usually we use it for metal, and RF usually for the metal oxides because of a better control of the process.
All right, thank you so much. Another question was regarding the purpose of adding aluminium grid on the top of the layer of the main layer of your solar cell.
Oh yeah, that's for. It happens actually. Honestly, it happens. Not we didn't do it purposely, but initially we wanted to make an alloy, copper, indium, aluminum, alloy. So it's alloy, but then we observed that actually the aluminum that didn't alloy, but it making alumina oxides. And then later on we found out that it's actually make a defect specification. So the initial reason is we want to make an alloy. But then we found out that actually it's making a defect specification. So yeah, there are two reasons. One is the actual reason is to make an alloy, which we didn't make it successfully. So, but then, yeah, it happens.
So it was an accidental discovery you made.
It's accidental, yes.
Nice.
It's accidental.
Okay, all right. We have another question, Dr. Wيلمان, in the chat. Is it possible to deposit materials, for example, copper SPS, using electrodeposition without sulfurization, using sulfur source in the solution instead?
Yeah, it's possible. There is also a report on that. In fact, also I did that as well. It's possible, a sulfur source or selenium source inside the solution. So we just do all together inside the solution. But the issue might be that because it's usually grown at low temperature, so it has low crystallinity. So we do need still additional treatment after that, the annealing. So yeah, it's possible to make, but maybe not as high quality as if we do it after.
Okay.
Yeah.
All right. Another thing, Dr. Wellman, why having oxygen is important in aluminium CISSE? You have mentioned the importance of oxygen.
Oh, on the AES spectra is it's a proof that we observe alumina IL2O3. So the oxygens there was just as a proof that we observe alumina IL2O3. So it's not that it's important, but it's as a proof that we observe the formation of alumina oxygen there. Yeah.
All right, thank you so much.
Yeah.
Another question was regarding the preparation of tin samples. Was there a special process for this type of solar cells?
Special process for what? Sorry?
Tin, to make the tin samples, transition electron microscope samples.
Oh, yeah, it's my college did that. So that's experiment did by as expert of TEM. So I'm not an expert of TEM, but there is the special treatment FIB. They cut it to make a thin samples, but I'm not an expert on that. So yeah.
All right, thank you so much. The last question we got, can you make a comparison between dye-sensitized solar cells and using metal thin films in terms of efficiency and preparation methods through your experience?
Yeah, the SSC I had experience on. It's more the SSC. It's true. It's more simple to do, more simple process to make, and from my experience, it's not. We don't need to do to use a more sophisticated machines like the sputtering or so on. So it's as far as the SSC is simpler to make based on my experience. But efficiency wise, the important part I think is the dye. So the dye, if we use a correct dye, and it will make a high efficiency cell. But if we use like a low cost dye, so I had an experience that we use dye from a natural fruit, dye from fruit that occur naturally, and it has a low efficiency. But when we change it to proper dye, that molecularly engineered dye, so it's then it's able to boost. So yeah, as far as the fabrication method is simpler based on my experience.
It is true. Thank you so much, Dr. Septina. We're
welcome.
very pleased that you actually accepted our invitation, and we would like to thank you again for that. We're going to end now the seminar, so if you would like to say anything before we end, you can have the mic and say it.
Yeah, I just say thank you all for inviting me, and yeah, it's a great pleasure for me to be able to present my work.
Thank you so much. We're more than happy for having this opportunity with you. All right, thank you so much, Dr. Septina, and thank you for the audience for your listening. Inshallah, we're going to have more opportunities in the future with you, Dr. Septina.
Thank you.
Thank you so much.
Thank you, sir.
Assalamu alaikum.
Walaikum salam.